Hello, and welcome back. Today we are going to be talking about the sine and cosine laws in MBF 3C. So today we're learning what is the sine law and what is the cosine law. And these are not the sine and cosine ratios. These are more complex formulas, but they are just formulas, right? Just like the ratios, we choose when to use them, we plug in the variables that we know, and we evaluate for the one that we don't know. How do you know you're good at using the sine and cosine law? First of all, when you can verify that they're true by investigating it using technology so that you know them and you know that in fact that they are true. And second, when you can describe the conditions that guide when is it appropriate to use the sine law? Under what conditions should you use the cosine law instead? And once you've figured out what's the best time to use which one, then it's time for you to actually use these laws to calculate sides and angles in acute triangles. So just to start us off here, O'Neill wants to label the sides of a triangle so that he doesn't have to say hypotenuse, adjacent, opposite, because those are all too many syllables. He just wants to use a single letter. So in this triangle, what letters would you use to label each of these three sides? One way that you can certainly talk about these is you could say that this line right here is the line BC. This line right here, the hypotenuse, this is the line AB. And this line right here is the line AC. But even that, using two letters, may be too much work for some people. Can we get that down to just one letter? You might think that you may want to label this side H for height. And that way you might label this side maybe like B for base. And then this side, D for diagonal, maybe. And then you sort of have to explain which side is which, like this is the height, this is the base. And it wouldn't work if the triangle was not perfectly on the ground with a 90-degree angle, right? If this triangle had a different angle here, then this would not kind of be the height. So you might run into problems with more complicated triangles, but for a triangle ABC, it would work. Is there a way that we could come up with a system where we only use one letter for each of these sides, and it will work no matter what this triangle looks like? What if, notice that every angle is touching two different sides, which means that one side is opposite every single angle. The hypotenuse is opposite the right angle. This side is opposite angle A. And so what if we use that idea to label these triangles? What if we say this is angle A, so the side across from it will be side A. And this is actually what we do in math. When we're using triangles, we say that an angle and its opposite side have the same letter. The angle, we use a capital letter. For the side, we use a lowercase letter. And that way, it doesn't matter what orientation the triangle is in. It doesn't matter which angles, is a right angle and which one isn't, or if there are any at all. Every triangle will work like this. Notice that this side B, well, right across from it would be side B. And right across from angle C would be side C. So the big idea here is, in a triangle, we want to try to use the same letter for each angle and their opposite side. The angles are capitalized and the side lengths are lowercase. And notice when we have this situation, we sort of automatically fell into this idea that a squared plus b squared equals c squared, right? That would still hold true. So we're going to start an investigation right now, and I'm going to invite you to go ahead and scan this QR code to use Desmos's Triangle Creation e-tool to create a triangle on a sheet of paper, and then copy and complete this chart below. For each row, you're going to create a new triangle. So I will help you out by starting you off with the first row, and then maybe you can go ahead and complete the rest of the table, okay? Once you're done, try to see what you notice from this exercise. So I'm going to scan this QR code, and I'm going to go ahead and go to Desmos's Triangle Creation e-tool. And this is sort of what it looks like. So here I can click and I can drag around these 3 points, and I can move them wherever I want, and the angles and the side lengths are automatically calculated for me. Okay? So I can say that angle A is 53 degrees, angle B is 76 degrees, angle C is 51. Or I can even go to the side lengths, and when I'm writing down the side lengths, maybe I'll just round them to the nearest hundredth. So side A is the side that's opposite angle A. That's this side right here. And I can see from the Desmos software that it is 1.57 units long. Next up, I want to find out what is the side length of B. B would be 1.91. C would be the side opposite angle C, so that would be this side right here. And I know that the length of this side is 1.54 according to the software. Angle A, like I mentioned, is 53 degrees. Angle B is 76 degrees. Angle C is 51 degrees. And finally, for the rest of the row here, all I'm going to do is I'm going to say, what is A divided by sine A? So I'll take out my calculator and I'll put in 1.57. That's side A. Notice it's a lowercase. 1.57 divided by sine of 53 degrees. And my calculator will tell me that that is equal to approximately 1.97. Hopefully you got the same thing I did, which is 1.968 or 1.97. What would go here? So this is C divided by sine of angle C. So I will take 1.54 and I'll divide it by sine 51. Hopefully you got 1.98 here. And that's all you have to do to fill out this table. The last column of the table, it looks more complicated, and it is. So I would definitely recommend that you use a scientific calculator, or even use the scientific calculator that you could find on Desmos's website to put all of this in. Take just a minute to see if you can do that by yourself, and we'll take this up in a second. So hopefully you were able to get 1.54 as your answer here. Or sorry, 1.53. And that's rounded up from 1.529. So what you can do is complete the rest of this table, right? Just move these dots around, these points, which will create a new triangle, triangle number 2, and then just fill out these 6 with whatever you get from here, and then fill out these by using your scientific calculator. So just continuing along with this investigation, I hope that all of you managed to get a chance to continue on and make 4 triangles of your own. I'll do a second one here, and we'll see if we notice any other patterns pop up. So first off, over here in my second triangle that I've created using the Triangle Creation e-tool, I can see that the value of A is about 3.10. The value of B, the length of side B, which remember, the side B is opposite angle B. So this is the side right here. That has a length of about 1.13. And finally, side C, which is this one right here, has a length of about 3.09. Angle A, B, and C are also given to me. And that's 81 degrees, 21 degrees, and 79 degrees. And I can fill out the rest of the table quite easily using these 6 values. By doing that, by taking 3.10 and dividing it by sine of angle 81, we would get about 3.138, and there's some more decimals after that, and we'll round that to about 3.14. So you should have gotten, if you did b over sine b, and so that's 1.13 divided by sine of 21, you should have gotten 3.1538, which rounds to about 3.15. And then finally, we have c over sine c, so that's 3.09 divided by sine of 79. So that would give me 3.1478, which we would round again to 3.15. And so these are our three values here, a over sine a, b over sine b, c over sine c. And the last column that we have to fill out is this large expression here, the square root of a squared plus b squared minus 2ab times cosine of c. And notice this c is a capital letter. That means we're going to use the angle, not the side length. What you should get if you do the square root of 3.10 squared plus 1.13 squared minus 2 times 3.10 times 3.10 times 1.13 times cosine of 79. Once you do all of that, you should end up with about 3.0903, which will round to about 3.09. Looking at these numbers, and hopefully you have at least two triangles of your own, you can look at your own table and at this one and see if you notice anything. Are there any patterns that are popping up to you? So some of the things you might notice are that these numbers are all really, really close. Notice we have 1.97, 1.97, 1.98. And so these are all really, really, really close to each other. In fact, I think the only reason why there's any difference in them might be because we rounded some of these numbers over here when we wrote them down, didn't we? Notice that our triangle has way more digits than we actually wrote down. And maybe if we included all the digits, we would end up with the exact same values. The other thing I notice is that when I did this formula, I did seem to get the same, or a number that's very close to the one in this column. Notice 1.54 and 1.53. For my second triangle, I also noticed these three numbers were again very, very close to each other. And again, this number was very close to this number. So I might say, even even given the fact that some of these decimals are a little bit off, I might say that I have verified one of the laws in trigonometry. In fact, not just one, two of the laws in trigonometry. And they are that a over sine a is equal to b over sine b and is also equal to c over sine c. If we had to give a name for that law, I think we might call it the sine law, because all of the equations here, all of the ratios use sine in it. The other law is that c is equal to all of this, right? Because look how close these numbers are. And I might call this one the cosine law because it uses the ratio cosine in it. So just to summarize that, the sine law is as follows. A over sine of A, so this is a side length at the top and an angle in capital letters, right? So the side A divided by sine of the angle that's opposite it is equal to another side divided by sine of the angle opposite that side. In fact, whenever you take a side and you divide it by sine of its opposite angle, no matter which side you pick in a triangle, you will always end up with the same ratio. The other version of the sine law is the flipped version, right? With the reciprocals of all of these. And the reason why we might use this is because in this version, the angle is already in the numerator. So if we were trying to solve for a side length, we might use this one. If we're trying to solve for an angle, we might use this one. Basically, what is this saying? It's saying that you can use the sine law to find an angle measure or a side length. You can use it when you have a pair. What is a pair? An angle and its opposite side. So if this was our triangle here, a pair would be these two right here. And then you just need one more piece of information, either one more side or one more angle, and then you can solve the whole triangle. You can find all the angles and all the measures in a triangle. The cosine law is given to you here. And again, there's two versions. One version of the cosine law has a side length already isolated for you. And if we were to take this and we were to try to isolate the angle, we would end up with this version right here. Both of them are basically the same law, just with a different variable isolated. So if you want to find out a side length using the cosine law, you would use this version. And if you wanted to find out an angle using the cosine law, you would use this version of it. You can use the cosine law when you have all three sides, right? Notice that the only variables you would use to input here are side lengths. There's no capital letters. Or if you have two sides and you have the angle that is contained in between those two sides, as follows. So if this is a triangle, two sides and the angle in between. If you know all of these values, then you can use the cosine law to find out the opposite one. Let's take a look at some examples so we can consolidate this information and see how it is in action. So we're going to solve this triangle. And to solve a triangle means to find out all the angle measures and all the side lengths. In this case, we don't know what this angle here is, and we also don't know what this side length over here is either. But it's pretty easy to find out this angle measure. We don't need the sine law, we don't need the cosine law, we don't even need the trig ratios. We know that all three angles, when we add them together, we should get 180 degrees. That's something that you should have been learning for quite a while now. So I can use that information. I can say, okay, if they all add up to 180, then if I start with 180 and I take away 40 and I take away 27, I'll be left with whatever's left is this angle right here. And that would be 113 degrees. So that's what I'll put here. Now that I have this here, notice that I do have lots of pairs in my triangle. I have x, angle x. I also have side x, which is 5, because they are opposites. That's how you make a pair, whenever you have two opposites. I have angle y now. I also have side y. So I can use the sine law for sure because I have many pairs. I'm trying to find out the length of side z. So, because I have x and x, which is the side and its opposite angle, I also have y and y, I can use the sine law. And this is the sine law. A side over the sine of its opposite angle is equal to any other side divided by the sine of its opposite angle. So I need to find z. What is the angle opposite z? Side x is 5 and angle x is 27. So I could just plug those in. Now, instead of using x over sine x, I could have used y over sine y. It doesn't really matter which pair you choose, as long as you choose a pair. So I've got z over sine 40, because angle z is 40 degrees, equals x, which is 5, over sine of angle x, which is 27 degrees. Now, how do I get z all by itself? All I have to do is multiply both sides by sine 40. That will cancel it out on this side, and when I multiply it by it on the other side, I end up with z equals 5 over sine 27 times sine 40. If you put all of this into your scientific calculator, you should get about 7.09306836. We're going to round this to the nearest millionth, and because a million has 6 zeros, that means we're going to use 6 decimal places, and that is the number 6 right here. Now the decimal after that is 8, so we're actually going to round this up to 7.079307. And that's the length of side z, which is this side right here. Angle PRQ. We have P equals 15 centimeters, R equals 19, and angle Q equals 50 degrees. we're trying to find out what is the value of q to the nearest centimeter. So here I have a triangle for you that's PRQ, where this side, which is side P, is 15 centimeters. Side R is 19 centimeters. So I'm just sketching this out. Notice that side P is opposite angle P. Side R is opposite angle R. And angle Q is 50 degrees. So I drew that right there. Also notice that I did not draw this to scale. This is not a perfect triangle. These side lengths aren't actually 19 and 15. But as long as it's sort of a triangle, I can still use it to solve for other side lengths, and then I can figure out the details later. Now I'm trying to find out what is the value of this side, Q. And because I have two sides, and I have the angle that is contained in between them, that tells me that I can use cosine law. That's side Q right there, and this is cosine law. Notice that I chose the version of cosine law that has the side isolated by itself, right there. Now, this is using A, B, and C, but my triangle is PRQ. Does that matter? Should I change anything around here? I don't think it really does. All this cosine law is telling me is that if I'm choosing this side, then this angle needs to be the angle that is directly across from it. So, if I'm trying to find out what is side length Q, then angle Q needs to be what I put in here. The other two side lengths don't really matter which one I choose for which. So this is my equation. Side length Q is equal to the square root of 15 squared plus 19 squared minus 2 times 15 times 19 times cosine of 50 degrees. And if I put this into my calculator, what would I get? Once you do this, you should get the answer 14.819, and there's a bunch more decimals after that, and we'll round that to the nearest centimeter, which is 15 centimeters. In this third example, we want to find out the measure of angle A, and we want to do this to the nearest tenth. So here I have an angle. I'm trying to figure it out. I don't know either of the other two angles, but I know all three sides. Now this kind of looks like a right triangle, but I don't know that it is. I don't know that B is 90 degrees. I'm not seeing a square angle there, and I'm certainly not seeing the value of angle B. So I can't assume that I can use the trig ratios. Instead, I can use the cosine law because I have 1, 2, 3 sides. And I'm going to use the version of the cosine law that has the angle by itself. The angle is nice and isolated. So all I have to do here is plug in the values of all the sides into here. So notice that this is angle C. That doesn't mean I'm going to plug in angle C. Remember, I'm looking for angle A. So over here, what I'm going to use is I'm going to put A. And then over here, where you see the side length C, that just means the side that is opposite this angle. And so I'm just going to put the number 4 into C. 6 and 7 will go into A or B. So this is more like what the formula that I'm using. Notice that they're all still variables. It doesn't matter which one you sort of put where, or it doesn't matter whether you want to change one to another letter, as long as all of them are, changing. So I've changed all the C's to A's, I've changed all the A's to B's, and all the B's to C. And so this version of the cosine law is much better because it helps me relate to this triangle. And once I plug all of this into my calculator, right, I plug in cosine inverse of 4 squared minus 7 squared minus 6 squared all over -2 times 7 times 6. I'll get 34.7719, which I'll round to just 34.8 degrees. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.